Okay, and I actually prepared a bytecode example to just show how a simple program which sums two numbers in Kotlin, for example, is compiled into a bytecode. That is the corresponding bytecode, a little bit cleaned up, and we can just see how it works. That just to compare it with a C-like model, which is gonna become useful later. And basically, it is more or less the same as what we've already discussed. And basically in computer science, this is the way that we execute programs. We have a place where you put code, a place where you put data, a heap that keeps adding things, and a stack for all the activation records. Okay, then now we're on to the platform code, and to understand how actually Kotlin code gets executed and gets lowered to an execution level. And it's a progressive, like we have to take steps to understand what goes on. Hi everyone, can you hear me fine? Okay, I'm Andrea Cioccarelli. I'm a Kotlin and Android developer. I graduated this year in school in software engineering. And I am the last thing standing between you and aperitivo, so I'm gonna try to make the talk interesting. And okay, I wanted to start actually with some motivation and why I'm talking about this specific subject. And it came up because I was doing some challenges in computer security, and sometimes you have to write in C, in the C language, because it is a very low-level language, and you can get very close to the machine instructions that get executed on the CPU. And you use that explicitly because it is fast, and you can do those kind of things. And while doing these challenges, I was cursing myself out because you don't have all the type safety that Kotlin provides, and you don't have all the runtime features and all of those things. And it actually led me to start to dig a bit deeper and understand what goes on between writing the Kotlin code and actually the Android application and the Android system executing it. And it turns out that there are a lot of things that go on between that, and that's what the talk is about, more or less. Another important point that I want to make is that more or less as developers, we model systems. And for example, when you write the application that you're writing, we model as a white box everything that you do. So you need to know your code, you need to know your libraries, you need to know your dependencies, and you come at conferences like this to learn more about how to build better applications. And then you also model other systems, for example, the operating system, you model the runtime, you model the kernel as black boxes, because you're not interested in how they work, you just use them while you develop your workflow. And that's exactly how it's supposed to be, since we're developing application, since we're on a platform which integrates really well with the language, where you can, for example, build the ChatGPT application in 2 months and ship it to 100 million users. But that's not the only way that you can do that. There are many projects, for example, the Linux kernel, which works very much on a lower level and is written all in C and runs on billions of devices. And you have other softwares like FFmpeg, for example, which is used for converting audio, videos, and everything like that. And that also is written in C and hand-optimized assembly. So you can get very low on the level that you work on. And my main idea is to give you more tools and a better view of the Android environment from the standpoint of how your code gets executed. We're going to go through a lot of technical sides, and I hope that you can learn something. But even if you know already every technical detail that I'm about to explain, I hope that I'm packaging that in a way which feels better and which gives you a better perspective as a developer and can make you write better code and just know better the system that you're designing. And I told myself I wasn't going to do this, but I'm going to do it. How many of you flew in to this conference? If you can raise your hand. Okay, quite a few. And now, subset of that, how many of you are nervous flyers? So, for example, you're not very comfortable going in a long-haul plane or those kind of things. Okay, just a few. Okay, it's fine. And that is the point that I want to make is that even, for example, outside of development, for example, pilots use the same approach. They use black box modeling for things that they're not really interested in, for example, aircraft engines or lift produced by the aircraft, and they focus on the declarative part. They are in the cockpit with knobs and dials, like we are in a language, for example, writing statements and doing high-level things. And they're not really mechanicals, they're not engineers, they don't go in how the things get actually physically executed. But again, a more experienced pilot has a better knowledge of the plane, just like a better experienced developer knows better how the ecosystem works. Okay, that was the introduction. The talk is divided in 3 parts. Well, actually, it's the same topic, the same root topic, but it's explored under 3 different lenses, if you want. The first one is specification, where we work with the JVM, because everything that we write, be it in Kotlin or in Java, actually has to go through the JVM, and so we need to look at that. Then we go into the platform, and we see how Kotlin code gets lowered until the execution level on Android. And finally, we take a look at some, like decompiling some language features and seeing how the Kotlin compiler actually implements them under the hood. So that's more or less the idea. Cool? Thank you. Okay, let me take a sip. Let's start with specification. We all start from the abstract JVM, which is defined in the JVM specification. It is an abstract computing machine, and it is meant to be an abstraction for your computer. Every computer has a different, some computers have groups of instruction sets which run their own assembly code and their own microarchitecture. And the JVM is a way to join them on a middleware level, where you can write the same code on a higher level and have it deployed on different systems which have different implementations on how that code works. It is a stack-based virtual machine, meaning it uses a stack. We'll get into that later. And it actually has only 256 instructions, which is why it's called bytecode, because it has 1 byte of operating code. And I don't like to quote usually, but I read the specification and I wanted to read that out for you because I think it's beneficial. And it says, specifying the abstract Java virtual machine serving as documentation for a concrete implementation only as blueprints document a house. An implementation of the JVM must embody the specification, but is constrained only when necessary, meaning that it's just the core points that need to be fixed by the language, the people that implement the language and people that implement the JVM emulator. And that is the more typical thing that you see when you work with the JVM. And you have all sorts of languages which target a platform, which is the JVM, which is language independent. The Java virtual machine, despite having Java in the name, doesn't know anything about Java or other languages. It defines an abstract specification, and then platforms implement a JVM implementation for a certain platform, traducing the class file, for example, to the actual instruction that run on that specific platform. And that's how you achieve the usual motto that you have with the JVM, which is write once, run anywhere. Now, yeah, that's what we said. CPUs have their own machine representation, and the JVM bridges that gap. On Android, we don't actually use exactly the JVM. We use a variation of that. We're going to get into that later. And it is heavily modified and optimized since, as the talk before me just finished to say, mobile devices are power constrained, are battery constrained, and are CPU constrained. And so the Android developers back in the day designed a specific runtime to be suitable for mobile devices. And that is actually a good approach for Android because it also supports a variety of different architectures. And so it makes sense to have a middle layer where you target your applications. For example, for Swift, since Apple has much more close control over which kind of device they produce, which kind of architecture they have, and which kind of code they ship, they can actually ship binaries instead of just packaged applications because they have a much more closed system. Okay. Now, the main thing that is given in the specification is the class file. A class file is just, either a class or an interface which just gets compiled. And it contains all the information that you need to run it for the JVM. And it's actually really simple in a binary structure. So we can actually look at the fields. They're not too much, and it gives you a better idea. The first 4 bytes are magic, which is that number. There's a nice story about that, but you can look it up, which is used to identify the format. Then you have the versions. You have the minor and major version, which tells you which JVM target you are compiling that class file for. Then you have the constant pool, which is basically where all the constant, be it like in numbers or strings or properties or other things, end up finishing in the final class file. And it basically contains everything, and it is all in one place. Then you have access flags, which are basically markers that are for the class. For example, public, final, abstract, synthetic means that it's not you didn't write the class, it's been generated by the compiler. Enum, which is actually the reason why Kotlin has the modifier enum class, because it's a class. And then you have this class and superclass, which are references in the constant pool on this class name and the superclass name, if it exists, so the class that extends that. Then you have the interfaces, which just lists all the interfaces that are being implemented by the current class. Then you have the fields, which basically does the same. It's all the fields that the class declares. Then you have the methods, and maybe it's gonna ring a bell if I say that the method, like the maximum count of method is 2 bytes, so it's like 65,000 something, and that is not exactly the reason why we have multidexing. It's similar, but like the idea is that we have a count which limits the amount of methods that can be in a class, so we need to split, for example, multiple classes when we target Android. Then we have attributes. Attributes are actually, I don't know why they're confused with fields. Attributes are just metadata that is embedded in the class that contains all the other kind of information that the JVM supports but is not contained anywhere else in the class file. For example, annotation or exceptions, or for example, debugging, like line numbers or those kind of things. They're meta information, they're not fields. And actually, attributes cannot be like, you can't put anything in there. They are just defined by the JVM specification. So, they're constrained, and that's gonna come later. Okay, then the JVM declares 2 data types, declares primitives and references. I'm sure you're very familiar with that. Primitives cannot be null. They hold directly the value that the actual property holds, and they're basic data types. Reference types are actually just basically, if you want pointers, they hold a memory address to the location of where the object being referenced is. And they can be null, as we all know. And actually, with primitive types, we have Java virtual machine instructions, which are differentiated based on the primitive that they target. For example, iadd adds 2 integers and in 1 integer. ladd adds 2 long values in 1 long value, and so like that. And so we had already a constrained instruction set, and we divide it further in different instructions specified for primitive types. So it's really narrow, the JVM instruction set. Then we have runtime data areas, which is basically what happens when you load the class file into memory. Just as of now, we discussed what happens when you compile it. When it gets into memory, you have the method area, which is basically where all the methods and fields and constructors are put, which is basically the program text. Then you have the runtime constant pool, which is basically just a constant pool put into a special place so that it can be accessed easily at runtime. Then we have the heap. The heap is the memory region in a Java program where we store variables, and they are instantiated when you use the new bytecode, which is the same as instantiating a new class, for example. And the memory reference that you get actually points to the heap where the object resides. Then we have the most important data structure that you have in the JVM, which is the stack. The stack actually is the stack in stack trace, and every function call that you make in a JVM program pushes a frame onto the stack with the arguments and all the local variables. And you keep pushing stacks until, for example, a function returns, and then it pops off a frame of the stack, and you go on with the execution. And actually, to keep track of execution, you use the program counter, which is a register that you have inside the, it's the only register that's in the JVM, actually. And, and it points to the method area, to the actually currently executing method. And also, we should mention that the JVM allows for multi-threaded applications. In this case, we can have two concurrent threads accessing, for example, the same class with the same methods. They have two different call stacks because they call different functions and two different program counters. Now, to get into a little bit more detail about how a stack works, a stack is divided into frames like that, and a frame is composed of local variables and operand stack. Local variables are basically initialized with the parameters of the function that is being called, and operand stack is, it uses tstore, and operand stack is where the actual instructions can load the data. Okay, and I actually prepared a bytecode example to just show how a simple program which sums two numbers in Kotlin, for example, is compiled into bytecode. That is the corresponding bytecode, a little bit cleaned up, and we can just see how it works. We have, before the first instruction, we assumed you have a frame on the stack, and the first two instructions push a variable onto the stack 15, and then they pop it to save it onto the local variables. Then it does the same thing again, pushing 10 on the stack and then saving it in the local variables so that we loaded the two values that we want to sum. Then we have two iLoad instructions which load them into the operand stack. It's called operand stack because its values are used as operand for bytecode instructions. For example, I don't have to specify on I_add what is going on or which parameters to sum because it sums the two topmost parameters on the operand stack of the current frame, and it puts the result on top of it. And iReturn does the same thing, basically. It returns the value on top of the stack to the caller function. I'm running out of water. Okay, another thing which is baked into the JVM is the calling convention. The JVM always calls methods with a pass-by-value strategy. So, for example, for primitive types, it's easy because the types are just copied over. With reference types, what is copied over is the reference, so the memory address of the variable on the heap that is being referenced. It is copied, so it is a copy, but actually you have the address of the variable, so you can still modify it. That, just to compare it with a C-like model, which is going to become useful later, C on Linux usually uses ELF executables, which are, it's a very extensible, it's called executable linkable format, and it's used throughout the kernel and throughout Android. And basically, it is more or less the same as what we've already discussed, and basically in computer science, this is the way that we execute programs. We have a place where we put code, a place where we put data, a heap that keeps adding things, and a stack for all the activation records. And that is just the same idea done for a C program, and you see that the kind of code, that is assembly code, but the same thing applies. For example, you have the add instruction, which it takes two registers, and it sums them, and then they are returned. The syntax is different, the platform is different, but more or less the architecture is the same. Okay. Then now we're on to the platform code, and to understand how actually Kotlin code gets executed and gets lowered to an execution level. And it's a progressive, like we have to take steps to understand what goes on. At the first step, we have the compilation. So we have the Kotlin compiler, and the Kotlin compiler actually is really good because it's divided in two compilation stages. You have the front end and the back end. The front end takes code and it verifies it. It builds a tree of all the definitions. It checks for errors. It checks for syntax. And once it's done, it produces an intermediate representation which sends off to the backend. The backend is the thing that targets different platforms. With Kotlin today, you can target the JVM, you can target JavaScript, you can target native, or you can target WebAssembly. And that is because the same IR, the same FIR can be interpreted in different ways and used to be generating different things. Now, we've had K1, which is the front end, for some years. Actually, this week, K2 became stable, so you can all go ahead and enable that. And the backends are that. Also, by the way, when I'm quoting, like, this is not my, like, I kind of copied this slide, and you can find the reference in the bottom right of the slide. And as Android developers, usually in the future, we're going to be interested in using K2 as a front end and JVM as backend. And that's more or less the idea. So that's how Kotlin compilation works on a super high level. Android expects an APK file. An APK file is just a zip archive, is nothing more. You can just unzip and is the same format. And it contains all the resources that you need for installing an application. And on installation, they're put in data directory. And then on execution, they are loaded. You have the Android manifest.xml, which defines the application and all the capabilities to the operating system so that it can check in install time what permissions are required, what target version the application needs, and all those things. You have resources, which is where all the XML and images and everything else goes. You have libraries, which are basically what the compiled binaries that your application ships. And you actually ship different binaries depending on which architecture you're targeting. The most common are those one, or ARM64. And then we get to the classes.dex. Now, we've seen up till now that with Kotlin, we get out classes file. And Android gets .dex files, which are Delvic executables. And it is a different format, actually. So why doesn't Android execute classes? The answer to that reason, why it uses a custom format, is because Android doesn't actually run the JVM. And that is actually, some people think it's like a proper JVM. It's not a JVM inside an Android device. And that leads us to the next step, which is ART, which is Android Runtime, which is basically the Android, if you want, virtual machine. It is an optimized virtual machine which executes classes.dex, and it is designed to be efficient on memory-constrained and battery-constrained devices, because the JVM is more general-purpose executing, and ART is more tailored for mobile devices. It is register-based, meaning that all the implementation that goes on in the specification of the JVM is not what actually happens in the DEX file, because DEX, for example, operation don't have a stack. They all have a register because that is more efficient on mobile devices. And they have a different bytecode. So we need a way, a tool, to convert from a class file, which gets out of Java and Kotlin, to a DEX file, which is actually ingested by Android and used to execute the application. This is just a slide to showcase the difference between the JVM and ART, is what we already said. And that the most important point is that we get out classes out of the JVM languages, and we need to convert them to DEX files to make them work on Android. And actually, thank you. Actually, the Android runtime was named something else before KitKat. Before KitKat, we used Delvic, which is actually the name of the virtual machine that gets, that was before. And then after Lollipop, we have ART, which is the Android runtime and is the modern solution. It is actually really sophisticated, and it changes on every Android release, basically. And that is actually the low-level part that we're going to get into. So we've said that Android executes DEX files using ART, which is the Android runtime, which is a simplification. It's not strictly true, because Android optimizes a lot of application even after they've been compiled and installed on the device. So Android uses a mix of just-in-time and ahead-of-time compilation to optimize application execution and to basically make your code run more efficiently on that specific device, because the way you wrote it in general maybe works like on a general representation, but maybe on some specific device, on some specific architecture, there are some optimization that can lead to much more like a better performance improvement. And the intuition is that if I have a compiled binary of the same application, it's going to run faster than the same counterpart executed on a virtual machine. So the main compilation types are ahead of time, meaning that all the code is compiled before application execution. And when compiled, I don't mean compiled by you in your computer before shipping it to Google Play. I mean, once it's been installed on the device, the binary gets recompiled to the architecture that the phone or the tablet is running. That is ahead of time. Just-in-time is something different because it runs compilation and profiling as the application is running. And then you identify, for example, methods that are hot, that are being used a lot, and you choose to optimize those, making like a selective choice and optimizing the most used methods. Actually, it's very tricky, and it's not the point of this talk to actually show you which kind of compilation is used, because it really varies on device. And if you, for example, if you recompile everything, it's going to run maybe faster, but then you have much more CPU usage because recompiling an application is intensive. You have more battery usage. The application takes up more storage since I'm recompiling all of it. And if I, for example, just recompile some parts, then maybe I'm missing out on some performance. So that is just for the low-level guys which are going to implement that. But the point is that when the application gets shipped to the device to be installed, it gets installed, and then it gets passed through a tool which is called the DEX to ODE. DEX is basically another conversion format. You switch from a DEX file to an ODE file. ODE is just a pun that someone made for, well, naming the thing. It just stands for ahead of time, meaning pre-optimized. And actually, the reason I've been stressing C and ELF binaries is because ODE files are actually ELF binaries. They contain the optimized platform code that the Android operating system can use, and as well as the non-optimized DEX classes. So there is actually a lower level, which is the ODE file format, which describes how applications on Android are on the lower level implemented. And it is a very poorly documented format for the simple reason that it changes in every release. Every time that you update your operating system, Android changes some, well, not every time, but potentially it can change anything in the way it converts ODE files. And that is why you have to optimize every time that you update your operating system, your applications. And when it says optimizing this application, it just means, okay, I'm regenerating the compile code to make this application run faster. And it changes because the DEX to ODE, I think I went back. No, okay, no, it's fine. And yeah, they are ELF files, so they are linked with the same binaries that is used to load up native libraries. So it works well and it integrates with the actual Android tooling. And that is a screenshot from a Black Hat talk, which shows for example, the way methods can be compiled. A class can be compiled. A class can be compiled with all the methods, so all methods in a class are compiled, meaning efficient. Some can be compiled or none can be compiled. So it selectively chooses methods based on its heuristics, which changes off frequently, and it makes them change. What actually goes on, to further optimize this, is profile-guided optimization, which means that the Google Play identifies across devices on a specific application version, which methods of that version are very intensive, and while the application is being sent for installation on the device, it also tells to the device, okay, this is a list of, for example, the methods. This is a profile that I'm giving you, and is a suggestion for the runtime to pre-optimize those methods because those are going to lead to the better improvement. Okay, that is just, now I prepared an overview of all the process that we've been through with flowchart, so that we can get a better idea of how it works. So we have Kotlin and Java classes. We compile them respectively with their compiler, Kotlin C and Java C, and we produce class files as output. Then we pass class files to D8 and R8. I think you're familiar with them because you have to configure them in build scripts and all that. They are built to, well, D8 is a dexer, meaning that it converts class files to dex files, and it's also a desugarer, meaning that it lowers language features. For example, you may be targeting a higher JVM version, and it lowers those things for the conversion to happen on the same way. So it gives you a way to work on higher level features, and it preserves binary compatibility with previous DEX versions. And R8 is an optimizer which removes things and optimizes code. Okay, then you get your DEX files, you join them with the resources, you join them with any native libraries and everything else that you can code in your application. They are all joined together in an APK file. Then the APK file is signed and zip aligned with your keystar, and that is more or less your job as a developer. Once you sign your APK, your Android app bundle, whatever you're doing, you send that off to the Play Store. Now, that is the whole scheme. Once the APK file gets to the device to be installed, the Android operating system pulls out the SO libraries, which are the native libraries, which puts on a side, and then it pulls out the DEX files. The DEX file is run through DEX2OD to compile it on the for the platform, and it contains the DEX some DEX executable and some optimized formats, and that is the way that it produces the OAT executable for that application. Then those things are passed to the runtime. The native libraries and the OAT part of the application are executed natively, while the DEX part of the application is executed during using the binary, which is the Android runtime, which is still called Dalvik VM. And the idea is that it uses continuous compilation and profilation, so you can, while you execute or while you update the application, you can get new compilation methods, and so you increase for example, the potential for the application. Okay, that is more or less everything with the Android platform specific, and now we're going to move on to the language features and how some of those things are implemented in Kotlin. Okay. Now, language features in Kotlin can be implemented basically in two types. When I mean language feature, I mean something on top of the JVM, because the rules of the game, if you want, for language designers when they implement Kotlin is make a new language that is as good as you can to code, but it has to adhere to all the principles and languages that go on in the JVM. So you can implement it either through the compiler with code generation and sugaring and rearranging methods and all that, or you can implement it with a type system which catches errors at compile time instead of runtime. And the only rules that you have when you're designing a language, like for backward compatibility in this case, for example, Java has a lot of backward compatibility requirements because there are millions of lines of code in Java written, so they can't just create a new syntax. Well, when Kotlin was introduced, it didn't have any backward compatibility issues, and so it could take advantage of years of language evolution to design a better overall language without being too much constrained on the backward compatibility. And yeah, and all this section is good for you if you think about how you would implement those features yourself if you were designing a language, for example, for the JVM. Okay, we're gonna assume Kotlin 2.0. We actually have a slide for Kotlin 2.1. We came out 2 days ago, so stay tuned for that. We're gonna be targeting the JVM as the backend for the compiler. We're gonna look at non-optimized bytecode the compilation to be just to showcase, and I've cleaned up all the samples, so if you decompile them yourself, they're gonna be a bit uglier, but for showcasing on a slide, I didn't want to clutter everything with bad code. Okay, so let's start with a simple Kotlin class, and just something that you want. It's the first thing that I thought up about a counter. And I was thinking about how you would implement that, how that gets compiled to Java. And now we're gonna see what that class compiled to Java and then decompiled from Java looks like. And which is basically the bytecode that is generated by the compilation process looked at from the Java language. And the first thing that sticks out is the metadata annotation. Now, actually, metadata annotation are attached to every class that you compile with Kotlin, because the reason that we went over at the beginning of the talk is that the JVM in the class format cannot store non-JVM specific formats or parameters. And Kotlin actually needs more parameters than the JVM allows. For example, you need nullability information. You need the information for declaration side variance or reflection or all those things. And you need to put them somewhere. And so they decided to go with an annotation that goes on every class. That's why the class names are so little, because since it goes in every class, you want to make the most that you can to not make it heavy and increase the code size. And also, class names in Kotlin are suffixed with KT to avoid conflicts of name. Okay, let's start with nullability, which is the biggest thing that Kotlin offers with respect to Java, and it's the main selling point. And the issue with nullability actually in Java stems from the fact that the JVM allows types to be null. It's okay for every type to be null at any moment. And the idea in Kotlin that it is not okay for all types to be null at any point. We can accept nullability and constrain it in the type system but we need a way to handle that. And in Kotlin, the type system handles the nullability explicitly, and it is safe by design. The code correctness with that respect is checked at compile time, meaning that all things are, if there is an error with nullability, we get it before the application executes. And this converts potential runtime errors, which are due to the JVM's unreliability with respect to null types, to compile time errors. Now, this is actually a piece of the Kotlin hierarchy that you can see. Kotlin actually partitions its type system in two parts, a nullable universe and a non-nullable universe. This is non-nullable, so it's C. And then you have the nullable counterpart, which is basically the same root, the same graph, but with question marks, meaning that the type can be either there or it can be null. And you have a subtyping direction from the nullable type to the non-nullable type. Okay, nullability creates basically a safe environment, and Kotlin provides a few operators that you can use to work with nullability. We have the safe call, Elvis, and the double bang, which are designed explicitly to handle those kind of scenarios. And we're going to look at how they get compiled. The safe call operator basically allows to make a call conditionally. If a value is safe to be called, if a value is not null, it makes a call. If not, nothing happens. And that is the way that it works. It checks for the variables. If the variable, in the compile code, if the variable is not null, it calls the accessor. Otherwise, it returns null. Then the Elvis operator is actually similar. It gives you a variable, and then you say, in case it's null, provide me with this default value. And it does the same. It checks if it's null, it gives you the variable, or otherwise the result. And I find it funny that both of those null-safety features in Kotlin are implemented in JVM in the code by a ternary operator. It's like Java telling Kotlin, oh, I have this. And then we have the double bang operator, which is basically just asserting that a type is not null at runtime. And that is compiled to a call to intrinsics.checkNotNull with the parameter. Now, that is self-explanatory. It means that it checks the nullability of maybe, and if it is null, it throws an exception. And the class intrinsics is actually part of Kotlin JVM internal, and it is sprinkled throughout the Kotlin code where it is necessary to check and enforce the type system safety at runtime. That can be useful, for example, for platform types. Because within Kotlin, the type system handles everything, and so you're okay, you don't need to inject those checks. But when you interoperate with Java, if types are not annotated coming from Java, you don't have any nullability information for a type. And so you cannot say whether it is nullable or it is non-nullable. Kotlin actually has a very elegant solution to this. It has gradual typing, which is a language feature, which is implemented in Java with platform types, meaning that any type which is not annotated from Java coming from Java can be, the type is between the type itself and the type itself, but nullable, which gives you a range. And that is actually implemented also in using the dynamic keyword for Kotlin JS. It is the same feature, and it basically disables type checking for that variable. That is an example of a class in Java. It has a bad method which returns null, and it has a good method which returns a valid string. Now, if you want to implement that in Kotlin, we can interoperate with Java. And in the first function, I declare the types as non-nullable, meaning that I'm telling the compiler, I know this is not null, and I'm accessing good and bad. And in the second call, I'm declaring them as nullable, meaning that I'm telling the compiler, this may be null, so make sure to generate the code accordingly. And the code that gets generated, actually, in the not null call, when I access the methods, since I declare them as not null, it generates an intrinsic.checkNotNull expression value, meaning that I said that is not null, thus I'm gonna enforce at runtime that this is actually a variable that is not null. And if it's null, I'm gonna crash at runtime because I made an assumption which is not verified. And if I declare them as nullable, the compiler doesn't generate those checks because I explicitly allow types to be nullable from the type system. And yeah, that's the exception at runtime. Okay, a question could be, why don't we treat platform types as just nullable by default? And the idea is that it's kind of painful to do that because you have to write a lot of nullity checks, which are mainly redundant for the Java code. And so Kotlin actually relinquishes a bit of type safety and gives you the authority to say, I know this is okay, I'm going to declare it as a normal type, and so I go ahead with this, or I'm not sure, I'm going to declare it with a nullable type, and I continue by checking. So among Kotlin classes, the type system enforces null safety, and in Kotlin interoperating with Java, the compiler inserts those intrinsic checks matching your type declarations. Okay, now we have when statements with enum, which I didn't want to add this because I thought it was trivial, but then I looked at the compilation and I was like, okay, that's kind of interesting. I think you all know what when expressions are, and we are going to look at them with enums. So for example, imagine you have an enum with 4 directions, north, south, east, west, and their number, and just a when, which gets the directions and matches all the possible directions, printing whatever it is. Now, if we decompile this, we get first the enum in Kotlin, which generates the things, and then some code for getting the variable. And it gets also a values synthetic method, meaning that it's generated from the compiler, returning basically an array of all the enum entries. Then it generates a Kotlin when mappings, which is basically a class that it declares a array mapping enum ordinals, meaning their position. So, for example, the first item in the enum is going to be 0, the second one is going to be 1, the third one is going to be 3, to their number. That is defined by the compiler, and for example, it maps the first element to 1, the second element to 2, the third element to 3, and so on. And it declares it as a variable in when mappings. And then, when you actually have the when statement, it gets the map from the when mappings, passing in the ordinal of the enum that you supplied. That way, it knows immediately which item you're going to choose. It matches it in the when expression, which is compiled with a switch statement, and then it goes executing, for example, this case, south. No, well, depends on the runtime, but yeah, it goes executing in the right case. And if not, throwing a no when branch match exception because we don't have we shouldn't get there anyways. And Kotlin introduced when guards in Kotlin 2.1, which is 2 days ago, which allows you to add a new check with the operation. So for example, if in this case I want to do path.dir.nord, if direction of the bearing is greater than 10 degrees, which is another condition, in this case it doesn't really make sense, but it's just to showcase. First, I add it with an if statement, and then I have to add an else because the when, in this case, is not exhaustive anymore. And that gets compiled to basically more or less the same code, but it gets an additional end check on the variable that we are adding the guard statement to. Okay. Okay, I think I'm going to skip properties because I'm kind of running low on time and they're basically trivial, so I don't want to bore you with those things. Okay. Extension functions, they're actually really simple to implement, and they're a simple idea, but they get integrated in the language in a very deep way. So just to declare a sample extension function, you can have a string, for example, .lastchar, which returns the last character of a string. And this gets compiled to a static method, which takes into the method the caller that we have as the first argument, and then it basically translates the call that we've made. And that is all compiled, meaning that when we access an extension function, it is actually putting in place that static call. Now, that is very nice on itself, but it comes really useful when you talk about Kotlin conventions, which it's really it shines when you have when you look at how Java implements those things. For example, how it implements iterable in loops for making items iterable, or auto-closable for try with resources, and it works by implementing interfaces. So once a class has been compiled, you cannot change it anymore because you cannot like change which interface it implements. Kotlin actually formalizes conventions, which is this way of integrating in the language with functions, with declaring functions with certain names. And that is actually really smart because I can declare more functions on an object by declaring an extension function. So I can take a Java class which has already been compiled and that I cannot access or modify, and I can declare extension functions on top of that, making that class more Kotlin-like and better to work with in the environment. And that allows you to enrich the existing classes with extension functions. OK, that is already said. There are a few conventions. OK, another convention that is really useful and works like it's used sometimes is Destructuring Declarations, which are implemented by defining just on a class the component n function, which is it returns the nth component of the class, and it's useful for extracting data fields from the class. That is, for example, how you can implement it in a point, which has two variables, x and y. You implement component 1 and component 2. And that is what actually gets generated as Java. You have the normal class with the getters. And then you have two functions, which are literally called component 1 and component 2. And then when in Kotlin you declare a function and you try to destructure that, actually what happens in Java is that they are two different assignments, and they are called the positional arguments with component 1 and component 2. And if you want to ignore an argument, the compiler just will not emit that assignment so that it removes that. Now, I'm running a little low on time. I don't know if I can continue. OK, 2 minutes. OK. I'm going to skip data classes because, again, they're basically pretty well known. I want to get to something more useful. OK, that is actually something that really surprised me while I was doing this research, and so I wanted to just give you like a little puzzle at the end. The JVM doesn't support default arguments for methods, and Kotlin actually implements like default arguments on top of the existing JVM. And so, for example, if you were to declare a method like that with padding, where you supply 4 default parameters, how like I want you to think, how would I implement that on a like how would I write the compiler to write that kind of method? The main assumptions is that it should replace the values that I didn't supply with the default that I specified, and it should also preserve interoperability with Java because I want the same function to be callable by Java. And that's actually done in a very smart way in Kotlin. That is the function that we've seen before. That is the function that gets generated, which is the same with the same body, and it doesn't have any additional default. But then we get another function, which is appended with the default name. And it has the same arguments that we have before, but it adds two more arguments. And basically, it checks whether the first of the new 2 arguments is ended with values. And if some values are specified, it replaces them with their default value, which is embedded in the padding.default class. And that is actually really nice because it generates a normal method to just call the class and a helper method to replace the class with their default parameters. And yeah, I think we're done. Yeah, the parameter that is added is a bit mask, and the value is 1 if the parameter is absent, and the value is 0 if the parameter is present. And so the compiler, when you call something with a default argument, is going to generate the appropriate bit mask given how many arguments you've supplied and which ones you didn't. And then when you call the function, is going to take care of replacing them. OK, that is me trying some things with many arguments. OK. And yeah, that's more or less the talk. Yeah, I'm done. Thank you.
Awesome. Massive round of applause, please, for Andrea. That was awesome. Wow. Amazing.
Thank you for the water.
Well done. Oh, you're welcome. You're very welcome. That was amazing. Holy moly. We could have listened to you till next Tuesday or something. That was amazing. And I feel like I don't know anything about Java or Kotlin anymore. It's amazing. Yeah, sorry we don't have time for questions, but you're here tomorrow as well, or amazing. So if you do have questions, which I'm sure you do, because I will be there tomorrow, like, find Andrea tomorrow. But that was awesome. Thank you so much, and really, really appreciate all your effort. Thank you so much.
Thank you
awesome. One more round of applause for Andrea, please.